Welcome! This is a lesson on dynamic programming, and we'll cover roughly everything you need to know to start solving problems. And before we start, let's do the prerequisite. The main thing you should already know is recursion, because DP solutions usually build upon recursive solutions. If you don't know recursion, you can still benefit from a good portion of this lesson, but it won't be truly complete without recursion knowledge. And if you need a good resource for that, check out the lesson from this course. Now, here's my effective resume in terms of competitive programming. I have about 3 years of experience in competitive programming, and I reached the rank of International Grandmaster on Codeforces and 7-star on CodeChef. In terms of Google stuff, I've gotten to round 3 in CodeJam twice, and my best rank in Kickstarter is 10th, which I also got twice by some coincidence. So yeah, the point of this resume is not to flex, because there's not really a point in doing that. I just want to say you can trust me. I know what I'm talking about. I'm not going to mislead or confuse you. And this lesson will be accurate, well thought out, and complete. And with that said, let's get into the lesson. But before we start the lesson, let me give you a quick overview of how this will be structured. We'll start with a brief overview of the big picture of DP, and use a carefully selected example problem to demonstrate the point of DP and its power. I'll go over both of the common methods of using DP, namely the recursive and iterative methods, and after that, we'll establish some vocabulary and tie it back to the example problem so you can understand it in context. Then I'll give you a couple of very useful methods you can use to start solving problems with DP, and we'll use 3 example problems to give you a bit of practice with those methods. I'll finish off by comparing the recursive and iterative methods so you can know which one is better suited for your current level, and I'll also briefly go over some more advanced forms of DP that you can use as a guide once you master the basics. Now, let's start with what is DP, because I think it's a good idea to start with the big picture so you can understand what this technique is and what we're really trying to do here. And the main trick of DP is, we're going to be solving problems recursively, via the recursive method of breaking down the large problems into smaller subproblems. In fact, we're going to be doing brute force recursively most of the time, but it's going to be a smart brute force. We're going to save time by not doing the same thing multiple times, and we'll do that by discarding useless information about the solutions generated by the brute force. Now that probably doesn't make sense by itself, so let me illustrate this with a problem. Say our task is to count the number of different paths on a grid from the red cell to the green cell, where you can only go down or right. Now first, let's imagine how a brute force would solve this. In this example, there are 4 total paths. A brute force would simply go through all of them and count each one. You don't strictly need code to understand this, but feel free to implement this brute force yourself if you want. And I'll show the code here too. You can pause the video and see that. But let's look more closely at this blue cell. There are 2 ways to get from red to blue, and for both of these ways, we're also going to take both paths from blue to green. But let's ask, why are we taking the blue to green paths both times? Because remember the big picture, we're discarding useless information. Once we get to blue, we don't care how we got there from red. All we care about is that there are 2 paths from red to blue. So let's compress both of the red to blue paths into a single path. It'll have something like a value of 2, which represents that there are 2 ways to get to blue. Then we can go from blue to green only once instead of twice, but we'll remember that there are 2 ways to get to blue, so each time we get to green, we can add 2 to the answer instead of 1. And that way we'll still get the 4 paths, but we'll do it a bit more efficiently because we compress these paths into a single path. And that's our other big picture idea, not doing the same thing more than necessary. We only go from blue to green twice for the 2 paths instead of 4 times. And okay, but that was a contrived example. That grid looked kind of weird, you know. So let's do it for a general 3x3 grid now. And here there's no clear middle point. There's no blue cell where we can use the optimization. But why not just treat every point as the middle point? What we can do is we can essentially treat every cell like the blue cell. And for each cell, our goal will be to count the number of paths that end at that cell. So we immediately know there's 1 path from the red cell to the red cell, obviously. What can we do from the red cell? We can only go down or right. If we go down, then we know of 1 path ending at that downward neighbor, where we go down from the red cell. So we can add it to that neighbor. And if we go right, same deal. We know of 1 path ending at that rightward neighbor. And we can process every cell like this. For each cell, figure out how many paths end at this cell. Let's call it x. Then if we go down, we know that x paths go through the orange cell and then go down. So we should add x to the downward cell, and do the same for the rightward cell. X paths go to the orange cell and then go right. So let's just run through this whole example really quickly. Each cell will be orange, and we will push out the number of paths from the orange cell to its neighbors. And here's what the code would look like for this. Again, you can pause the video, I'm not going to dwell on it. So it should make sense why this is correct, at least, right? Maybe not why it's Maybe not why it's like fast, but it should make sense why it's correct. Because we're still doing the brute force. The only difference is for each cell, we're compressing all of the paths that lead to that cell into one single path. For each path, we're discarding the information of how we got to the ending point because it doesn't matter. All that matters is where it ends, meaning that we're allowed to mash together all the paths that end at the same point. And we're actually solving the assigned problem for each cell instead of just the green cell. And that's kind of the recursive way to think about it. We just solve the same problem for every cell, and we use the answers of the smaller subproblems to build up to the larger subproblems. And the number of possible ending points for paths is just the number of cells. So it should make sense that the time complexity is the number of cells, because that's literally the only information we have about the paths. And there's one more thing I should note. When we push out the answer from a cell to its neighbors, we need to make sure that our answer for that cell is correct. That is, we need to have pushed the answers from all the cells that affect this cell, which in this case are the upper and left neighbors. For this problem, going through the cells in row major order is fine, because we can only move down and right. But for other problems, the necessary order may be more complicated, so be careful about that. And one more thing, if you're familiar with graphs, you can think of these push relationships as directed edges in a graph, where the states are nodes. Then the order that you have to visit the nodes has to kind of be a topological sort of this directed graph. But in most problems, it's going to be as simple as going from smallest to largest or largest to smallest, so don't worry too much about the ordering stuff when you're starting off. And that's it. That's DP. This this explanation may be hard to generalize, so I'll run through a couple more practice problems later in this video. But if you're comfortable with recursion, I'll also show you a different method that you might find easier to use or more intuitive. Now again, think about how you would brute force this recursively. It would essentially be backtracking, starting from, say, the ending cell, and computing the number of paths for each cell computing the number of paths that end at each cell. If you didn't have it before for the iterative solution, I would recommend having code for this, so you can try to code it for yourself or just see the code from before. I'll show it again here. But we can do an optimization here that's pretty similar to the iterative method. Let's look at our contrived example again. The compression would actually be the exact same. For each cell, we compress all the paths ending at that cell into one path, representing the number of paths ending at that cell. So instead of all the paths, we just have the number of paths. And of course, we can do this for every cell as well. Implementation-wise, it's not actually much different from the recursive code itself. And I want you to try and think about how we can do this. Actually pause the video and figure out how we can manage to go through the red to blue paths once. Okay, hopefully you paused. If you didn't come up with anything, that's fine, because we're all here to learn. And the trick is, let's remember the number of red to blue paths after we compute it for the first time. And we'll remember the answer for every cell too. That way we compute each cell's answer exactly once, and afterwards we can just return the value that we remembered. So this is what it would look like in code. As you can see here, we're storing this extra right answer that represents the answers that we remembered from previous previous cells that we visited. Now, this is called memoization, and it's not a typo or a verbal typo. And don't ask me why it's named that instead of just memorization. But the complexity analysis and stuff is pretty similar to the iterative version, so I'll just leave it to you to figure out. And by the way, you can convert between recursive and iterative pretty easily. For example, to convert from recursive to iterative, just change the parentheses to brackets and put in a loop. Simple enough, right? It's also worth taking the time to relate this method to the big picture ideas. In this case, we're once again able to get rid of the information of the paths themselves. All we care about is where the paths end. We're allowed to only compute an answer for an ending cell once, because that answer will be the same answer no matter how the rest of the path will be. And if you want a bit of practice, here's a variation of this problem. You still move on a path from top left to bottom right, and you can still only go down or right, but now each cell has a value, a number. The cost of a path is the sum of numbers on the cells you visit, and your task is to find the minimum cost over all paths. For a problem like this, you would compress the possible paths into not the number of paths, because we're not trying to count anymore, but the best possible path, like the path with minimum cost. So if you end up trying this, good luck. Alright, before we get into more problems, let's establish a bit of vocab related to the grid problem so you can understand it in context. If you want more examples of the vocab, you can check out the section with more problems that comes later in this video. So the first thing in the vocab is the state. The state essentially represents the values that the discarded information was compressed to. It also just represents the subproblems we solved to build up to the main problem. In the grid problem, this is just the cell. because we compressed all paths ending at that cell into just the number of paths ending at each cell. So the only information that matters is the ending point, which is the cell. The next thing are transitions, which represent how states kind of interact with each other. In the grid problem, the transitions are represented by moving down or right. So for iterative, the transition will be pushing the answer from cell RC to R plus 1C and RC plus 1, aka down and right. And for recursive, the transition is taking the answers from R minus 1C and RC minus 1, aka left and up, or up and left, respectively, and adding them to get the answer for cell RC. And similar to recursion, there are base cases. These are the easiest type of states which we already know the answers to. In the grid case, the base case is the starting cell, which has exactly one path. You can also consider the edges the base cases because you have to treat them special and make sure to avoid an out-of-bounds error. And also similar to recursion, DP always needs base cases or there'd be no starting point for our answer. And here's a bit of vocab that can further distinguish the two methods I talked about earlier. There's pull DP and push DP. In pull DP, we essentially pull from previous DP values to compute the current one. In pseudocode, it's structured like, for each state x that we're trying to compute, for each state y that can affect x, so for all the states that x depends on, do some transition with dpy to dpx. Or do some, like, for example, you can add dpy to dpx or do some min-max shenanigans. It all depends on the problem. So we're pulling the information from the y states and using them to figure out what the x state is. This was equivalent to our recursive solution. In contrast, push DP is more like taking the value of the y state and pushing it to all the x states that it affects. Pseudocode is something like, for each state y, for each state x that it affects, do some transition with dpy to dpx. So we're pushing the information from the y state out to the x states that it affects. This was our iterative solution. I personally find push DP a lot more intuitive, because usually in a problem you can do something to the state. For example, you can move around or add an element onto an array. When you do an action, you modify the current state into a new state. Then you would naturally push the current state value onto the new state, because you just went from the current state to the new state. But when you do this with pull DP, you kind of have to reverse the actions. So you would maybe have to move backwards or remove an element from the array and do the opposite of what the problem statement tells you to. This personally feels more confusing to me, but it does allow for the usage of recursive formulas, so it can also be useful. And since I just mentioned it, recursive DP can only be pull DP. Because think about trying to use push DP on our grid problem recursively. If I push the starting cell to the cell on the right, and then visit that cell, then maybe I'll visit the orange cell next, because that's how recursive DFS would work. But that orange cell doesn't have the answer from its left, so we'll think it only has one path, which is wrong. For pull DP, this is fine, because we can just recursively compute the answer if we don't know it. And for iterative DP, the order always matters, because we can't just recursively compute the answer like I just said for iterative DP, because iterative can't make use of recursive function. So if we do pull DP iterative, we also have to make sure that our order is fine and the answers we pull are complete. Alright, we've established our vocab. Now I'll give you some tips to help you start off with solving DP problems. And the first question you might have is, how would you recognize that a problem is solvable with DP? My answer to that is just intuition. You'll eventually just have a DP radar, kind of, where you can roughly tell if DP applies to a problem or not. And that radar comes with practice. But if you don't have it yet, I'll give you an alternative instead. Whenever you try a problem, like any problem, just ask yourself, can it be solved with DP? Because you don't have that radar, you don't know if a problem is DP or not, but you can try it anyway. And just assume it can be solved with DP and try your hardest to apply DP to the problem. And if you succeed, great, you solve the DP problem. And if you don't, it's quite possible that it wasn't a DP problem at all. And that's fine, you still learn an example of when DP doesn't work, so you're getting better at it either way and you're getting the practice in. And if you thought it wasn't DP but it is, that's kind of problematic, so spend some extra time thinking about what you missed and how you could have come up with the right solution. Another perhaps obvious question is, how do you actually solve problems with DP? There are two main ways you can go about doing this. And the first is, think about how you can solve the problem recursively. Remember I mentioned at the beginning, DP is basically just recursion. So think about how you would solve it with like a brute force or backtracking as a first step. If your answer is a sequence of moves, process it one move at a time. If you're given an array, process the array one element at a time. Stuff like that. You end up breaking the problem into little bits and solving one bit at a time, then passing off the rest of the problem to another recursive call. That's how you think recursively. That's how you solve problems recursively. And once you have a recursive solution, that usually tells you the state and transition. For example, here's some code that demonstrates how you can get that information. The state, in this case, is given by the parameters through the recursive function. It's just the cell, and the transitions, the moves, are given by the recursive calls you make to smaller states. And if you add in memoization, you'll often just have a solution right there, and that's what we did for our recursive solution to the grid problem. But it also gives enough insight for you to be able to solve it with the iterative method too, if you want practice with that. And if there's no obvious recursive solution, there's another way to find a DP solution. Often, you can pull the state and transition straight out of the statement. Like, there aren't that many possibilities for what can be part of the state. And the state usually represents a smaller version of the main problem you're solving that you use to build up to the main problem. So wouldn't it make sense that the state might just be the problem you're solving? As long as you make sure you're getting rid of useless information, you can often just get the state right out of the problem statement. And you can get the transitions in a similar way. If the problem allows you to do something like move around or change something about the state, then that usually takes you from one state to another. And that's what transitions are, so you can figure out the transition from what the problem asks you to do. And if neither of those methods work, chances are it's not an easy DP problem. So you're probably going to have to be able to conceptually reason about DP problems and come up with something smart to solve it, which you'll only be able to do with practice. If you get the practice in, you can solve anything. And speaking of practice, here's an extra problem. You may recognize it, you may not, but either way, it's fine. So pretend you're a frog. You start at position 0 on a line, and you're going to go to position n. In one move, you can either jump 1 unit to the right or 2 units to the right. And similar to the grid problem, we're going to count the number of different paths you can take from 0 to n. So right now, take some time to pause the video and try and solve this for yourself. This could be called easier than the grid problem, but it also might not be, so don't worry too much about the difficulty for now. Just try to solve it. Okay, hopefully you paused. So let's first ask, what information is important about our path? And what information isn't? Is there some defining feature we can compress all identical paths into a single state? And with those questions in mind, how would you solve this problem recursively? Just try writing a brute force first. If you want, you can spend some more time thinking about these questions. So pause the video, you can come back right now. Right, so the state should just be our position in our current path. We don't care about how we got to this position. All that matters for the future is that we're here. Very similar to the grid problem, since nothing to the left can restrict our movement to the right, so we don't care about anything about a previous path. The only thing that matters, again, is our current position. And what about the transitions? Well, those are given directly from the statement. We can either move 1 or 2 units to the right, and both of them are almost always valid options. So our transition should be adding together the possibilities of moving 1 or 2 units. If you wrote a recursive solution, it probably looks something like this. It doesn't have to necessarily look exactly like this, but it could look similar. You'd be using memoization, and you'd be counting the number of paths starting from 0 and ending at the value pause. You can move 1 or 2 units, so you can either come from 1 unit to the left or 2 units to the left, meaning that you sum the number of paths ending at those 2 positions. And if you wrote an iterative solution, it's probably similar to this. Since the answers for positions rely on positions to the left, we would iterate from left to right, starting with 0 at the base case. And that way, when we compute the answer for a position, we've already computed everything to the left of it, meaning we've already computed the answers that this position depends on. So if we know that there are x paths to position pause, then we know of x paths to pause plus 1 because we can jump 1 unit on each of those paths. And we know of x paths to pause plus 2 because we can also jump 2 units. In either case, the state is still the position and the transitions are still jumping. Now, relating this to our big picture ideas, we optimize this brute force by compressing all paths with the same ending point into a single path. And we don't process any ending point more than once because we don't care about how we got to a particular ending point, only that we got there. And by the way, this problem is equivalent to the Fibonacci sequence. If you recognized it, good job. Yeah. Okay, here's another problem. We'll just do knapsack, which is very common. You have an array of numbers of length n and a target value t. You want to answer, is it possible to select some of the numbers from the array so that these selected numbers sum to t? And here are some examples of when it's possible and not possible. So you can again pause the video, spend some time to try and solve this one. Okay, hopefully some time has passed. So let's start with the basic methods again. It might not be immediately obvious how to get the state from the problem statement because there are a lot of options. There's, for example, you could have n in the state, you could have t in the state, you can have all combinations of selected elements in the state. So let's try the other method of just writing a recursive brute force. And we can ask the same questions as the last problem to help with thinking about a recursive solution. As mentioned before, to solve array problems recursively, we usually handle the problem element by element. Again, you can pause the video here if you want, you don't have to. Okay, so we look at the first element. Do we select it or not? If so, our target sum goes down by that element because we just made progress towards the sum. We made progress towards the sum with that element. We're that element closer to the target sum. So if our element was 3, we're 3 closer to the target. And if we don't choose that element, our target sum is the same. But either way, we should move on to the second element because we made our choice about the first element. We decided what to do, either we took it or not. So we never need to process that element again. And we can do this for each element. We make our choice about whether we'll take it or not, and we move on to the next element. So the state for our recursive solution is the current element that we're considering and our current target sum. And the transitions are, we can either take our current element or not. So now we have our recursive brute force. And here, it's simple enough that we can just add in memoization and be done. Here's the recursive code for reference. I'm not going to dwell on it. And if you want to do it iteratively, we still handle it element by element. But unlike the other problems, here we won't push the number of solutions to the new state because we're not trying to count. All we're pushing is that now it's possible to reach that new state. And also note that our current state has to be reachable for us to be able to push to new states. Because otherwise, it's already impossible, and we're saying that other things are possible from this impossible to reach state, which doesn't make sense. And again, let's relate this to the big picture ideas. We don't care about the actual elements we use to reach a certain sum, so we can discard that information. All that matters is that we got the sum and that we made our decisions about a specific number of elements. So we don't process any combination of sum and number of elements more than once because we don't need to. We're processing every state exactly once. Another thing. This is another kind of trick that you might want to use. You can convert basically any 2D DP problem into a grid problem. Like for example, in this problem, you can simulate your actions as moving in an n times t plus 1 grid. Taking an element x is moving down a row in x columns right, and not taking an element is just moving down a row, as you can see by these arrows. Now your task is just to see if it's possible to hit the bottom right cell, similar to our grid problem, except now it's just asking if it's possible. And this isn't that revolutionary of an idea, because this is just how you'd be representing the problem with a 2D array anyway. But if this is easier for you to visualize, feel free to think about other problems this way too, representing it as the 2D array of states. If you want an extension to this problem, there are a lot of variants in Knapsack. I encourage you to search them up and try them for yourself. And here's the third problem. It'll be quicker than the other ones. It's the same grid problem, except this time you can move in all 4 directions, and you have to visit each cell exactly once. That is, no cell can be revisited and no cell can be unvisited. Your task is still to count the number of valid paths from top left to bottom right, except you have these extra restrictions. As usual, spend some time and try to solve it. Okay. And yeah, I'll show you these questions if you want. But yeah. Okay. Hopefully, you didn't spend too much time. And the reason being, it's not actually solvable with DP. I figured it's a good idea to make you spend time on a problem where it's not possible, because it's good to build intuition on when DP does and doesn't work, as I mentioned earlier. You should be trying to build that radar up as soon as possible. So, let's think about why it doesn't work. In the original grid problem, we can compress paths with the same ending point because it doesn't matter how we got there. This is because there's no restriction on how we can move that's based on our previous moves. Our previous moves don't matter in determining how we can move in the future. But in this problem, our past moves do matter because we have to visit each cell exactly once. So we can't just represent this path by its ending cell, because we need all the information about our path to determine how we can make our next move. So DP doesn't work here, and the solution is actually basically just optimized backtracking. There's not much better we can do. But yeah, it doesn't work because the information about our path is important this time. So our big picture idea doesn't apply here because there's no unimportant information to get rid of. All of the information here is important. Alright, I'll also quickly go over the advantages of recursive DP and iterative DP. I would personally recommend learning both because both have their advantages, but if you want one formulation to really focus on, fine. You can practice whatever you prefer from this list. So recursive is nice because it's basically just recursion with a few extra lines thrown in, like the memoization lines. If you already know how to solve problems recursively, and you hopefully do if you're this far into the video, then recursive DP isn't much extra work. You just memorize your states and call it a day, right? And also, unlike iterative DP, you don't really have to worry about the order that you use to go through states. With iterative, you have to make sure that for each state, you don't compute that state until you've computed the states that that state depends on. That's a lot of state, sorry. With recursive, the order takes care of itself because if you don't know something, you can just recursively compute it first, then head back to your current state and use that information that you just computed. When you get to complex problems like DP on graphs or trees, this can make it a lot simpler. As for why iterative DP is nice, for one, it's just faster. Recursive DP is slow because it makes a lot of function calls, and it can't benefit from fancy compiler optimizations that only work for like loops. So for some problems, iterative DP can be over 5 times faster. I've done those measurements. But usually it's very simple problems, and usually time limit won't be an issue until you get to later problems, but it's good to know that iterative will probably be faster. And it's also more versatile. For example, you can do both push and pull DP with iterative, but you can only do pull with recursive. And there are certain optimizations of DP that can only be done with iterative, though those are mostly beyond the scope of this video. And that's like mostly it for comparison. In general, recursive DP is good for people who are new to DP, but familiar with recursion because it's not so different and you can get the big picture pretty quickly. Iterative DP is kind of a different style and it requires more work to use, but it's more powerful and more versatile, so it's also necessary to learn eventually, especially as you get into more advanced problems. And finally, here are some extensions of DP. I'm not going to spend too much time on each one because I'll go into more detail in another lesson, but I'll give a brief overview of the different types and some problems to demonstrate how they work. First, a very general version is quote-unquote reconstruction DP. This is not an official name by any means, and it just means DP where you have to reconstruct the answer. For example, in the knapsack, it means you'd have to output the entire valid subset of values. You'd have to output your chosen elements, not just whether it's possible to reach the target sum. And the way this is usually handled is by storing the choice you made at each state to make it possible, or to reach that state. For example, for the knapsack, you would store not only whether that state is possible, but also whether you took the last element or not. You would store the choice you made about that element. And that way you can go element by element, and you can go backwards through your states and figure out your choices for the whole array, meaning you can reproduce the array that you chose. Another thing is DP on trees. This can involve problems like, of all paths that go through the root of the tree, you want the one with the maximum sum of values. Just an example problem. I'm not going to discuss the solution here. You can also have DP on directed acyclic graphs. For example, you can be given a DAG and asked to find the longest path on it. That's a pretty common one. There's stuff like digit DP. For example, you can count the number of numbers between some L and some R that have each digit appear an odd number of times. There are other optimizations. Specifically, you can optimize the DP transitions. You can use, for example, a segment tree or the convex hull trick. I have a video on these two tricks specifically, so I will just link that one. And there are also other optimizations like divide and conquer and the Knuth optimization, which I'm not going to really talk about here because I don't know them. Moving on. If you want more problems to practice on, just check out the website in the description. It'll have a sizable list of extra problems you can try out. And yeah, that's it. Hopefully you got a good idea of how DP works and how you can start to solve problems with it. The good and bad thing about DP is it's mostly just practice. Your skills can mostly only come from practicing it. I personally like to describe it as a mindset because it's kind of just a strategy for thinking about problems in a certain way. And you have to strengthen that mindset with practice. And some people say it takes a while to understand, but then suddenly it just clicks and you'll immediately be a god at solving DP problems or something. I honestly don't remember what my own experience was with it, but one thing is certain, if you practice it, you'll get better. And one more thing. In terms of this video itself, I put a lot of care into it, maybe more than it shows just from these slides, but I really hope this tutorial came out good. Like, this is actually the second revision. I rewrote about 80% of this because it kind of just wasn't that good. So hopefully this version is good. I'm going to try and maintain this level of quality throughout the rest of the course, and yeah, I hope it'll continue to be great. That's all. Goodbye.